Okay, the reproductive property of the Poisson. What is that? So let's think about having two independent Poisson random variables. So we have X Poisson with some parameter mu, Y Poisson with parameter nu, and X independent of Y. Let's define Z to be the sum of X and Y. The question is, what's the distribution of Z? So let's calculate then. Probability Z equals K. How do we calculate the probability that Z is equal to K? Well, we're going to have to, again, there's really only so many tools at our disposal when we work in probability. As we do more and more, we develop more tools. But right now, one of our biggest tools is conditioning and using the law of total probability. So let's condition on the value of one of the variables and see how that changes the values of the other variables. Okay, so condition on the value of X, probability that X plus Y equals K, given that X is equal to J times the probability that X is equal to J. Well, if X is equal to J, then this is equal to the probability that Y is equal to K minus J, given that X is equal to J, times the probability that X is equal to J. By substituting in, well, if X is equal to J, we can substitute J in for X. Okay. And then realizing that the left-hand side here, this conditional, this event only depends on the variable Y. This condition only depends on X, and X and Y are independent. So it's probability Y equals K minus J, probability that X is equal to J. And then also then realizing that, well, if J is larger than K, then this is the probability of Y being less than 0 equal to some negative integer. And Poisson random variables can only be positive, not negative. So this is going to actually run from J equals 0 to K. And now we can just substitute in what we know of the mass function of the Poisson. So for Y, it's nu to the K minus J, e to the minus nu over K minus J factorial, mu to the J, e to the minus mu over J factorial. All right. So now let's think about this. Let's define a value lambda to be mu plus nu. And let's think about pulling out lambda to the K, e to the minus lambda over K factorial. And if we pull that out, it means we have to put something out, put everything in its reverse order. So we end up with K factorial on the top, lambda to the K on the bottom, e to the lambda on the bottom. But e to the lambda is e to the mu plus nu. And we have, or e to the minus lambda on the bottom. So e to the minus mu plus nu, and we have e to the nu and e to the minus mu on the top. So we're going to get some cancellation here. So we're going to have to rework things here. And now what we want to do, well, let's do the cancellation and let's throw some stuff out. So K factorial, K minus J factorial and J factorial. That is all together, K choose J. E to the minus lambda cancels with these two. Nu to the K minus J and sum of the denominator, we have K minus J and J in the denominator. K minus J plus J is K in the denominator. So we end up with nu over lambda to the K minus J, mu over lambda to the J, right? And that's coming from those pieces there. And so altogether, when you realize that this is the PMF of binomial n and mu over lambda, because mu over lambda plus nu over lambda by definition is 1. And so that's the sum over all possible values. I'm sorry, it's binomial k and mu over lambda, but it's the sum over all possible values of a probability mass function. It sums up to 1, and what we're left with is lambda to the k, e to the minus lambda over k factorial, which implies that the sum of two independent Poissons is itself Poisson, and the parameter is just the sum of the parameters. Okay, so another way to revisit, so if we revisit the number of deaths in the city example, we should not assume that everybody has the same probability of dying. Okay, instead, what we should do is we should divide the city, divide the population into homogeneous groups or semi-homogeneous groups. And then within each subgroup, the number of deaths is approximately Poisson. And the different subgroups, for the most part, are approximately independent. So we end up in pretty much the same place, because we end up where by the reproductive property now, the total number of deaths is still approximately Poisson. And the mean equal to the total expected number of deaths per day. So there's actually no change in this approach. So we get the same answer, incidentally, which is pretty interesting given that you would think that the approach was the same. But this is going to lead us to a general approximation theorem for the Poisson, which we'll talk about next.